Sir, you don't have a solutions video for the trig integrals, right?
Yeah, sure. The homework?
Yeah, the homework. I was looking at it. Doesn't look like you do. I was just entering my that integral into math, or what is it called, Wolfram Alpha?
Mm-hmm.
Some of the solutions they're the same, but they just write them differently.
Yeah, you got to be careful with Wolfram Alpha because they'll simplify. They'll use all these weird identities that you wouldn't even think to use. These are the solutions.
Okay, yeah, I wasn't. Yeah, I didn't see them. I don't know why. I guess it's just not showing on my part.
Yeah, they should be there. 6-2. There's 2 parts. It's what, almost 4 hours of video? Yeah. Okay, it is 1 o'clock. So are you all ready to get started? We've only got 12 people here so far, but we've got lots to do today. So we started last time talking about trig integrals, and we're going to continue with trig integrals. We're not quite getting into trig substitutions yet. Hopefully today we will. But we just talked about how to deal with trig integrals involving sine and cosine last time. So we did these 3 examples here. And now we're going to proceed into the steps for solving trig integrals that involve secant and tangent. So just like we did when we were talking about sine and cosine, to start, we have to go in knowing a few things. Like we needed to know the antiderivative of sine, antiderivative of cosine, and then how putting a number in front of those x's really doesn't change anything other than us having to scale things. Similarly, with secant and tangent, we need to be familiar with the fact that the antiderivative of, where's my thing? The antiderivative of secant squared, x dx, is tangent, and that the antiderivative of secant x tangent x is secant x. So we need to have that knowledge going into this. Is everyone clear on that? Since the derivative of tangent is secant squared, then the opposite is true. And since the derivative of secant x is secant x tangent x, the integral is the opposite, right? So we need that going in, and then just throwing a number in front of those, all we have to do is just scale those answers. Okay, with that said, what is going to be—
that needs to be expected of us to know that as 2 + 2, 4. Those, those 2 equations.
Yeah, these 2, yeah. Just like you know that the antiderivative of cosine of x is sine of x.
Mm-hmm.
Those 2, same thing.
Okay.
Yeah. Okay, now, the strategy for doing integrals that involve tangent and secant, again, there's a set of steps, and this is on that formula sheet that I've given you to have on the test. So it's right here. These steps right here. So for these, we're going to be using, it's just these two scenarios that we're going to have, where with sine and cosine, we had 3 different scenarios that we looked at. Here, there's only 2. So let me go ahead and copy this over, and we'll just use this as we're working through the problems. All right, so let's go ahead and do this first one. I'm going to move this to a different screen. I'll just copy it over here. Oh, come on. Okay, so the first integral we're going to do, let me paste that thing in here. All right, here we go. So we're going to be working on the integral. We've got tangent to the 4th x secant to the 4th x dx. And so we look at these steps, all right? Obviously, this is a trig integral. We've got tangents and secants involved. So we go to the first step. If the power of secant is even, right? The power of secant is even, which we do. We have a secant in there, and it's even. So we're going to continue with this procedure. what we're going to do is we're going to save a factor of secant squared. And that means we're going to peel off a secant squared. We're going to peel it off to the side, just like we did when we were doing sine and cosine. So I had secant to the fourth, so I'm going to write it secant squared times secant squared. So that's me forcing a secant squared to the outside. And the thing that you want to be thinking is that you know that secant squared is the derivative of tangent. So now what you want to do is try and get everything else in the integral written in terms of tangent. And you know that if there's any secant left, right? If there are any secants still here, it's got to be it's got to be an even power, because you started with the assumption that secant was even. So if you peel off two factors of secant, you should still have an even number of secants there. Do y'all agree with that?
Mm-hmm.
Now, had we started with secant squared, right, just secant squared here, then we would have had a basic U substitution just to start, because the derivative of tangent would have been secant squared. So it would have been more straightforward than we have here with the secant to the fourth. So because we know that this is going to be an even power, we're going to use the Pythagorean identity to rewrite that in terms of tangent. So we're using this identity, 1 plus tangent squared x equals secant squared x, right? That's written right here also in the notes, but that's the one I'm going to use. So I'm going to replace that secant squared with that. So I go ahead and replace it. I still have the tangent to the fourth x, and now in parentheses 1 plus tangent squared x, and then I keep this secant squared as secant squared because, again, that's the derivative of tangent, so I want to have it there. And now I can just do a basic U substitution.
I have a question.
Yep.
So in order to break it down so that you could have used the 1 plus 10 square identity, so you would have you broke it down into two separate parts.
Yes, I broke it in. You mean I broke it into secant squared, secant squared?
Yes.
Okay, so the main reason I did that is to have the part in yellow, because that's the derivative of tangent. And so what was left, I needed to convert over to something with tangent in it. See, the yellow part's already taken care of. That part's going to be over here. This is going to be my du. See, when I let u be tangent, the derivative of that is secant squared x dx, which I actually have. Like, it matches up perfectly. Well, here, right?
Yes, so I understand. So in order to do the U substitution, you broke it down.
Yep.
Like we used to do for the 5 powers. Okay, I understand that.
Yep. Okay, so the yellow part's gonna be replaced with du, and then let's see, these parts in green, the tangent here and the tangent here, those are gonna be replaced with u's. So my integral is gonna look like this. Integral, I'm gonna have u to the fourth, don't forget that's tangent to the fourth, so u to the fourth, parentheses 1 plus u squared, and then everything in yellow is just du. And now we have a nice polynomial. We can distribute the u to the fourth through the parentheses. And then once we're there, we just integrate term by term. Just power rule on each one of those. So I've taken the antiderivative. And then my last step would just be to replace the u with tangent x. And that's it. Okay. This is the first example. It's pretty straightforward. We have an even power of secant. We peel it off. We peel off a secant squared. We get everything written as tangent, and then we just do a basic U substitution. Any questions?
Yes, I have a question. So you were mentioning earlier, if the secant was not odd, No, if the secant was even, then we can go directly to basic substitution.
Yeah, so like, well, no, I said if it had been the power 2. So let's say that the original problem was this. So I changed that's a 2 now instead of a 4, right?
Mm-hmm.
Now you could still peel off a secant squared. You could, because you have one there. But if we just take a step back, this is just basic U sub. U is tangent. The question is, do you see something in its derivative, right?
Yeah.
So I see that if I let U be tangent, the derivative of that is secant squared. So I can rewrite this as U to the 4th du. And I'm there already. Does that make sense?
Yeah, now it does.
Yeah. Okay, let's look at the next one. And you know what? I'll keep this here. Bring this with me. Okay, so the next one we're going to do is tangent to the 5th x secant cubed x dx. So now we have our secant is not to an even power. So the first step here is, you know, if the power of secant is even, right? We don't have that. We're not going to do this then, right? So what about if the next thing to check for is if the power of tangent is odd. Now we do have an odd power of tangent, don't we? So what we're going to do is we're going to save a factor of secant tangent. So we're actually going to peel off one factor of tangent and one factor of secant. So when I peel off one of the tangents, it's going to become tangent to the 4th. I'm also going to peel off one of the secants. So it's going to become secant squared. And I peeled off both a tangent and a secant. I'm going to write it this way: secant x tangent x dx. Right, so I just peeled one of each factor off. And the reason, again, we do that is because this in yellow is the derivative of what?
Secant square?
Oh,
Tangent.
just the,
Oh, secant.
right? The derivative of secant x is secant x tangent x. So now what I need to do is I need to take everything else that's here and get it in terms of what? Tangent or secant?
Secant?
Secant, right? Because the derivative of secant's sitting there in yellow. So I just need to make sure everything in blue there has secants in it, not tangents. Now, the secant squared that we have here, I don't even have to worry about, because it's already secant, right? It's really the tangent to the 4th that I have to change. And I know that it's going to be tangent to an even power. I know it's tangent to an even power because the step said if tangent was odd, right, to start, and I peeled one tangent off, so I know that what's left has to be even, right, an even power of tangent. That make sense? So now how do we rewrite tangent to the 4th? Well, again, we can use the Pythagorean identity. 1 plus tangent squared x equals secant squared x. But this time, because we want to rewrite tangent in terms of secant, I'm just going to subtract 1 from both sides. So everywhere I see a tangent squared x, I can replace it with secant squared x minus 1. But I don't have tangent squared, right? I have tangent to the 4th. So this is where you have to come in and rewrite tangent to the 4th as tangent squared squared. And then you still have secant squared, and you still have secant, and you still have tangent dx. So the only reason I did that is because I want to be able to replace a tangent squared with the secant squared x minus 1. So I have to rewrite tangent to the 4th as tangent squared squared. And we did this back with the cosines and sines last class. So
So
go ahead.
like in the part where it was tangent to the power 5 and secant, like initially in the question, couldn't we just like take the like break down secant into secant square and secant to the power 1, and then use U substitution rather than using this identity?
Okay, so let me get back and let me see if I understand your question. Could we have taken this and left the tangent alone and broke the secant cubed as a secant times secant squared?
Yes.
Okay, let me do that. Secant times secant squared x dx. Are you trying to do what we did before, where we're going to use this as our du? Like our
Yes.
derivative? Okay, so secant squared is the derivative of what?
Tangent.
Tangent. Okay, I agree. So we have tangent here, right?
Yes.
Okay, but this secant x, you've got to get it rewritten in terms of tangent. And the problem is that it's secant, not secant squared. So you can't use a Pythagorean identity. See, it's not an even power of secant. So this method won't work, or the previous method won't work for this scenario because you'll get hung up on that secant.
Yeah,
Make sense?
I understand. Yeah.
Good question. Good question. All right, so I'm going to keep going here, right? Everyone okay with this step? I'm going to make a basic U substitution now. U is going to be secant x. And I know the derivative of that is secant x, tangent x, dx. That I have. And then everywhere that I see a secant x, I'm going to replace it with the U. U squared minus 1 squared times U squared times du. So the yellow here, and then these are all, those are all the green pieces. And now you've gotten into a polynomial. Once you're at a polynomial, it's just a matter of simplifying this. So I'm actually going to FOIL this out. I'm going to expand U squared minus 1 times U squared minus 1. And if I did that, I could do it on the side. I'm just going to do it in my head. That would become U to the 4th minus 2U squared plus 1. And then I still have a U squared on the outside of that. Then I'll distribute the U squared through. And at this point, I'm ready for power rule. So 1/7 U to the 7th, but I'm going to go ahead and replace the U right now. Minus 2/5 U, which is secant x, to the 5th, plus 1/3 secant x, but to the 3rd power. I think I've got it all there, plus c. So you want to make sure that when you're working these problems, that you follow these directions, because it will lead you to the correct U substitution to make. If you get hung up and just do one of these and just try and stick with one, it'll work on some, but others it won't. Right?
On half of the problems. So on this transformation, on the box, on the blue box that you have in there, Professor? No, up there,
Yes.
yeah. So we had originally secant cube, and then we transform it to secant square, and then the secant that we left hanging, it's just that one?
Yes. This one.
Also,
here.
we took one secant and one tangent
That's right.
from each side. Okay,
Right.
now I get it.
Yep, we pulled one secant and one tangent because we wanted a secant tangent, secant x tangent x dx, because we wanted to make a substitution of U being secant so that its derivative was sitting there. So all of this is just trying to get to basic U substitution, but we're trying to force the derivative of the something. Remember, we always want to see something in its derivative.
Yeah.
We're trying to force that something's derivative to be there. So we're just kind of being clever in how we pull things out. And the power on the trig function is what determines what you're going to peel off.
So last time we did the sine and the cosine, and today it's like tangent and secant. So what is it under the 6.2?
Well, 6.2.
Okay.
Yeah.
Because I think in order to apply these rules, we need to understand the the syntax for the power rules and all that's right there.
Mm-hmm. Yeah.
What page
Jay-
is that little snippet you have? Do you know what page that is?
This,
Yeah.
what page it is in the book?
Yeah. You said it was on the formula sheet or was it on the book?
No. Okay, so in Canvas, right? If we go to Canvas, there's, I have under files, let me just go to it real quick.
Okay.
So if you go to files, and this is going to, this looks a little different than it will for you. Let me just go to student view. Yours will look more like this. You go to files, and then you'll see formula sheets, right? Click on that, and then you'll see here trigonometric integrals and substitutions.
Okay.
Click on that, and that is the sheet you are allowed to have on the test. Now it has what we did last time and what we're doing right now, and the stuff that we're going to do in a little while, this right here, trig substitutions. So this is going to be a very useful sheet for the next test. So make sure you get a nice hard copy of it. Okay, however, between now and the next test, because I'll allow you to have it, but you can't be referring to your computer for it.
Well, we need it for the homework, right?
And while you're at it, just go ahead and get all this stuff, because all this stuff you'll need for all the exams. If you're going to go make copies or have copies done, just download all of it.
Thank you.
Okay. Okay, so let me bring the notes back over here because I kind of like the wording of things here in the notes. All right, here we go. So I'm continuing. We just did these two examples. Now, at this point, you should be able to attempt a lot of the homework problems. Let me just give you kind of a warning, all right? Not a warning, more of a tactic. If you ever are doing a problem and you just get really hung up on what you're supposed to do, try turning everything in terms of sine and cosine. So like if you have secant in the problem and you're trying to work through those steps and they're not working, instead of writing secant, write 1 over cosine. And if you have cosecant, write 1 over sine. And if you have cotangent, rewrite that as cosine over sine. Does that make sense? Try and get everything changed to sine and cosine, and then try and use the steps that we have for sine and cosine. It's just kind of like if you're ever stuck, try that, all right? Okay. Moving on. We're still in trig integrals. There are other cases of trig integrals which aren't as obvious. For some cases, we need knowledge of common identities, maybe integration by parts, and just some, your favorite word, persistence. All right, so we're going to take a look at 3 interesting integrals: tangent x, secant x, and secant cubed. Whoa, where'd that go? All right, here we go. So we're going to try and find the antiderivative of tangent x, dx. Now, would you agree that this is a trig integral? I mean, it's an integral that involves a trig function, right? Does it fall into the categorization that we just talked about here? Let me erase all this crap.
No.
Do we have secant to an even power?
No.
No. Do we have tangent to an odd power?
Yes.
We do, but we don't have any secants. See, the first step to this says to pull a secant and a tangent out. But you don't even have a secant, do you? Right?
No.
So you can't follow this. So even though it is a trig integral, it's not falling into that format for that little cheat sheet thing and the steps and procedure how to do this. So again, this is where I would say, if you're stuck, rewrite this in terms of sine and cosine. So tangent x is sine x over cosine x. Do you agree? And now just go back and think about all the things that we've learned. What can you do? Go through your little Rolodex in your mind. Y'all know what a Rolodex is? A Rolodex, this is like old school. I mean, I shouldn't even use it. I've never used a Rolodex in my life, but Rolodex, what is that? Okay, here we go, images. So this is a Rolodex. Rolodex is like old school that you used to have on your desk. And then it had all these little, you could put like business cards, people's phone numbers, and you just like turn through it and find what you're looking for, right? So when I say the Rolodex in your mind, I'm talking about all the little things that we've learned, and you're kind of like, okay, power rule, you know, all these different things, basic U sub, integration by parts, you know, you've got all this stuff now. So when you look at this, anybody see it?
Is it just basic U sub?
Okay, what would the U sub be?
Cos?
Cos, all right. So you see that the derivative of cosine is negative sine, and you see a negative sign there, right? So we could just rewrite this as, this might make it, this might be helpful for everyone to see. If we just peel that sign off to the side, we can see that the derivative of cosine is there. And we're off by a constant, right? That's okay. So this looks like this is shaping up to be not too bad. I'll just multiply both sides by -1. And now I think we can just rewrite it, right? Integral 1 over cosine, which was u. And then we have a negative. Oops, I should pull that negative out. You know what? I'll put the negative. I'll just put it there for now. Du. All right, so what is the antiderivative? I'll put the negative on the outside. What is the antiderivative of 1 over u du?
ln?
Natural log. Okay, so we get negative natural log absolute value of u plus c. And then negative natural log of u was cosine x, plus c. And that's it. That's our answer, yeah? Now, I didn't tell you this, but if we go to our formula sheets, this is actually there. On our regular formulas, the 6 pages or whatever, if we go and we look at the antiderivatives page, this is reference page 6. If you look here, starting with formula 6, antiderivative of sine, cosine, secant squared, cosecant squared, secant u, tangent u. Okay, number 12, look at number 12. The antiderivative of tangent of u is natural, uh-oh, did we mess up? We didn't mess up.
Uh-oh.
We didn't mess up. They're saying the answer is natural log of secant, right? That's what they're saying? Okay, so we're saying it's negative natural log of cosine. So think back to this property of logs. You remember this property of logs from college algebra? That if you have a power on the argument of the log function, whatever's in there, like x to the n can come out, right? Well, you can go backwards too. You can take this negative out here and treat it like a -1, and then move it up to the power on the cosine. So it becomes a natural log absolute value cosine of x to the -1. Now you have to be really careful here because we don't mean inverse cosine. we mean cosine raised to the -1. And anything raised to the -1 is 1 over that. So this is really natural log of the absolute value of 1 over cosine x. And what is 1 over cosine?
Secant.
Secant, okay? So our answer looks different than the books. I mean, this answer up here is correct. It's not incorrect, just looks different than the book. And now we see where it came from. So again, moral of the story here is not every trig integral is going to be able to be done with those things that you just got, you know, the little cheat sheet thing. But just take a step back, rewrite everything in terms of sine and cosine and hope for the best, right? Just go through that little Rolodex in your mind. Okay, let's do the next one. Okay, now this one, I wouldn't expect anybody in this, no, it's just secant x, sorry, I wrote the wrong thing down. This I would not expect anybody to be able to get, okay? This is a very difficult problem. So I'm showing you this more to just show you how somebody figured this out, okay? Because it's pretty cool what they did. Let's go look at the answer first, because we actually have the answer on our formula sheet. And by the way, if you ever get to a test or something like that, and you have like the antiderivative of tangent on the, and that's where you are in the test, you can use the formula sheet. You don't have to go through the work. If it's on the formula sheet, you can use the formula. All right. So do you see here the antiderivative of secant by itself is this natural log of secant u plus tangent u? See that? We're about to show where that comes from right now. All right, so again, I'll be clear. Would not expect anyone to figure this out. Somebody spent a lot of time trying to figure this out. And here's what they determined. And this is going to be completely awesome, but completely like, wow, okay, I wouldn't have come up with that. So they said, look, after maybe years of trying, I don't know how long it took someone to figure this out. They said, I'm going to take this and I'm going to take secant x and I'm going to multiply it times 1. Oh, and I should also say here on the side real quick, had I switched that to 1 over cosine x, remember how I said switch everything to sine and cosine? If I switch it to that, that's what secant is, you're stuck. Like, you can't do that U substitution anymore, because if you let U be cosine x, the derivative of it's not there, right? The derivative of cosine, negative sine, it's not there. So you'd pretty much be stuck there. All right. So this person, what's that?
So in the part where you say 1 over cosine, what if you do integration by parts on there, not just U sub?
Okay, so if you did integration by parts, what would you?
So I would take cosine, convert it to a secant, and put it as the U.
Okay. And
And then
dx, right?
Yes.
Okay, du would be secant x, tangent x, dx, right? That's the derivative of secant. And then you got to go up here, and this is going to become x.
Yes.
And so your new integral, voodoo, right? I'm just looking at voodoo. Forget the ultraviolet for now. Just look at voodoo. It's x, secant x, tangent x, dx. And this integral isn't even a trig integral, because it's got an x in there too, right? So how do you do that one? So maybe you can try integration by parts again, but trust me, this will lead you down a very long winding road, most likely to a dead end. But it's something that you know, whoever was trying to figure this integral out originally tried a lot of different things, right? They tried the integration by parts, they tried weird substitutions, they couldn't get it to work. And what finally makes it work is this, and it's brilliant, but it's frustrating, because it's hard to see how you would ever come up with this. Okay, so now I'm going to multiply by 1. You ready for the 1? Here it is. Secant x plus tangent x over itself. Secant x plus tangent x. Right? Like, who in the hell comes up with that? Like, that's the one. That's the one we're going to use. Now, what's awesome about this is that if we distribute this secant through the top, we get secant squared x plus secant x tangent x all over. The denominator is now secant x plus tangent x. Who sees it? What now?
You can factor out a secant from the top and cancel out the top and bottom.
You could, but then we'd be back to where we started,
Yeah,
right?
you're right. Sorry.
Yeah. So algebraically, we can do that, but we'd be back at secant.
Can we use that secant and tan property that we just learned?
Well, maybe, but that was if we had secant and tangent together, like multiplied together, where we could peel off a factor. This is a ratio. We've got secants in both the numerator and denominator. They're separated by addition, so there's nothing easy we can do to peel things off. It's
Do U sub?
okay, what U sub?
Secant square. Make it U.
Anybody see it?
Would you split the secant squared into secant x?
You could do that, but it's even cleaner than that. I mean, it truly is just a basic substitution. Kelsey, you see it?
Secant x?
Do you use the identity for secant squared?
Oh, like use a Pythagorean identity? You don't even need that.
Isn't it just secant x? Let u equal secant x?
Not quite. Your basic U substitution, you're looking for something in its derivative, right?
Tangent?
What's that?
Is it tangent?
Well, if you use tangent, the derivative is secant squared, which I see as secant squared, but it's not really like by itself that I can peel it off to the side, can I?
It'd be the whole top.
Close.
It'd be the whole bottom.
The whole bottom is
Secant
U.
x plus tangent x.
Yeah, the whole bottom is U. Secant x plus tangent x. Okay, what's the derivative of that? Well, what's the derivative of secant x? You can do these separately because there's addition between them, right? Derivative of secant x is secant x tangent x plus what's the derivative of tangent x? Secant squared x, right? Dx. That's the whole frickin' numerator. Right? That's exactly the numerator. Now, I mean, the order is switched, but it's addition, so that doesn't matter, right? And then the denominator is U. So all you get here is integral 1 over U du. And the antiderivative of that is just natural log of the absolute value of U plus C. But U was secant x plus tangent x plus C. And that's the formula. That's what you would have seen in the formula. Whenever I see things like this and I show them to you, I can't help but think about the suffering that someone went through to get to that point where they finally had that moment where they figured it out. Like, this isn't really following any method we've learned, right? This is just someone was persistent and persistent and persistent and finally figured out multiplying by this really clever 1 works. But that's on your formula sheet, right? So you can use that. You don't have to go through this whole thing. Okay, one more.
Sure.
Integral secant cubed. So let's see, can we follow the steps here? Okay, it is a trig integral, right? Secant cubed is a trig integral, it has secant in it. Secant's not even, right? So we don't have that. And tangent's not odd because we don't even have a tangent. So we can't use this. I hope y'all are seeing like this right here is not like the magic pill that helps us solve every trig integral, right? It helps us in certain cases, but not all the time. So we can't use any of that, right? Now this one is not a hidden one. This is one that you can all do right now. You just have to get the right approach. So why don't I let you all think about that for a minute. See if you can't maybe figure out how to go about it.
Can we break them into secant square and secant 1?
Yeah. That's a legal move, right? I mean, you're allowed to do that. Do you want me to tell you whether or not that's the right way to go, or you just want?
Yes. Can you tell me?
I'm not going to. Okay, now what?
Now convert it into in terms of sine or cosine? I mean cosine.
Oh, you could, okay, so rewrite it as like 1 over cosine times 1 over cosine squared?
Yeah, but it's going to be the same thing.
So do you want me to or not?
I think I'll just swing, so yeah, I think you should.
Okay, I'll put it here. Anybody else, feel free to jump in if you have a different sort of path you want to go down.
And now use the trig identity about the cosine 1 minus sine square.
Everything that you've done is legally, you're algebraically, everything you've done is legal, right? So I guess this is the question. You're trying to get from point A to point B, right? And this is a problem, you know, that we see in math a lot. There is a way to get from point A to point B. There's like a shortest distance, a clean path. Right now, everything you've done is right. But what I'm not telling you is whether or not your path is headed this way or not, right?
Mm-hmm.
You may be going over here right now, which is fine if you eventually get here, but I'm not even telling you. You've done nothing illegal at this point. So you are on a path. You are on a path. I just don't know if it's going to get us there. As soon as you break a rule, though, as soon as you do something algebraically that you can't do, then you're no longer able to get from point A to point B unless you actually make a mistake, like make a second mistake to get you back on a path.
Or could we do that, like instead of doing 1 over cosine, could we just use the property in the formula sheet, the secant that makes the L natural log of secant u to the 10u? Could you do that?
No, because you have a product here. So you can't do them separately. I don't know if that's what you're asking me. Like, can you just look at what's the antiderivative of that and what's the antiderivative of that separately?
Okay, yes.
Yeah, we can't do that because of the product, right?
Mm-hmm.
Is it possible to use
Anybody else?
Is it possible to use like tangent square minus 1 equals secant square and change it?
Sure. So I'm going to go, we have one path is here, okay? Another path that we're suggesting maybe is to go here, secant x, and then I think what you're saying is to replace secant squared x with tangent squared x plus
Minus
1
yeah.
dx, I think. Is that correct, Abe?
Mm-hmm.
Okay, so that, again, that's legal.
What if we distributed the secant x?
Like this.
Yes. And then
That's legal, right? Let's do that. Secant x tangent squared x plus secant x dx. And then what, Minato?
what if we no.
Why no? Why did you say no?
I was gonna say pull off a tangent, but then we'd be left with this jumble of tangent times tangent plus secant x. I was gonna take the tangent plus the secant and then try to do something with that, but
Well, couldn't we split this into two integrals right now? Like we could do two, right? Because there's a plus sign between those.
Mm-hmm.
we could,
And this one, I'm gonna just put a check mark because we just did that one,
right?
right? And it's on your formula sheet. So really the question would be, can you handle this one? That's kind of where you would be, right?
Right.
But I think you're gonna wind up getting stuck.
Hmm.
So all of this that we've done, the part in blue, the part in green, these are all legal. Everything is legal up to this step, up to these steps. Any other paths you want to go down? Somebody have any other suggestions here? I wish we had just like an infinite amount of time to go through this material, you know, where we could sit here and just like do problems all day and, you know, like really get here and think and talk and try. It's just unfortunate. We just have so much to cover. We can't. So I'll give you another maybe minute or two for someone to either continue us down the blue or green path, or someone suggests something down that orange path. Okay. No? So I'm going to tell you what to think about now, and then I'm going to give you a few minutes to think about it.
Oh. So could you use U as secant square and the dv to be the secant x?
You could do that. What would be the other way?
The other way would be taking the secant x to be the u and the dv to be the secant x square dx.
Okay. So why don't you sit there and think about those two possibilities right now and see which one makes more sense to you?
I think the first one, because because I think the reason I have to do it is to get the power to eliminate in order to get, I mean, we need to reduce the powers, right?
Well, I mean, ultimately you just need to be able to do it, right? Like you need to be able to get to an answer. So we have two integration by parts things to consider. One of them is to let this be secant x and this to be secant squared x dx. The other option is to do it the other way around. Secant squared x here and let it be secant x dx there. So we have option A and we have option B, right?
I think we could do A as well because it'll be just 10.
Let's do a poll from the class. Do 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 Okay. A lot of people are saying let's go with A. So why? Why A? Anyone want to justify their position as to go A?
Because the derivative for secant x is just secant x tangent x dx. And if you try to integrate the secant, it's just tan x.
That's the part to me that's attractive, is the fact that the antiderivative of secant squared x is just tangent x. Like, I like that. Where over here, if we do it this way, think about what this would be. We have to take derivative of secant squared. That's chain rule. So we got to do 2 comes out first, the power comes out. Then I take derivative of secant x, which is secant x tangent x dx. And then I have to take the antiderivative of secant, which took us like 15 minutes to do anyway. It was like natural log of secant x plus tangent x. And that was just some miracle someone else came up with. And then my voodoo is just complete chaos, right? I mean, look at that voodoo. No, thank you. Look at the voodoo here. It ain't that much better, but it sure as heck is better than option B, right?
Yeah.
So the more of this that you can kind of like see before you actually start putting things on paper, the better off you are. Like, if you can see that option A was the better way to go, that just saves you time. You might actually do option B, but you have to at some point give up. Like, you have to say, okay, hold on, I got to try the other way. Okay, let's go. Let's continue down. We're going to take this integral, and we're going to go integral secant x times secant squared x dx is equal to, according to the integration by parts for A here, it should be ultraviolet, which would be secant x tangent x minus the integral of voodoo. So voodoo is our diagonal here, and that becomes secant x tan squared x dx.
I think we have to do it one more time in order to get it to the part where we can subtract the integrals with each other and move it to the left.
So you're thinking like those integrals we've seen before where it appears on the other side and then we move it
Yes.
to. Okay, so yes, that's actually what's going to happen, but we actually don't need to do another integration. So this part right here is just, yeah, it just is. Okay, look, this is secant squared x minus 1. Now I'm using a Pythagorean identity. I'm just rewriting tangent squared x as secant squared x minus 1. Now, why is that going to be useful? Because if I now distribute this through, I get secant x tangent x minus integral secant cubed x minus secant x dx. And now I'm going to split that into 2 integrals. Okay, so that became a plus. Be careful with that plus sign because I had to distribute the negative through there. Everyone follow that? It's just algebraically, I'm just splitting it up into 2 integrals now. Now remember, that's equal to the left-hand side. The left-hand side is this, which is really integral secant cubed. That was the original problem, right? And so hopefully you see that the original integral is showing up over here. And it's being subtracted. So I'm going to add that integral to both sides. So now we'll have two of them, won't we? On the left-hand side, we'll have two of these integrals equals secant x, tangent to x. This went away. And then we still have an integral to do, the antiderivative of secant x, but we already did that. That was a previous problem. And plus c. One more thing, right? Divide by 2. So I'm just gonna put a 1/2 in front of this, and I'm gonna put a 1/2 in front of that and get rid of the 2 over here. So the antiderivative of secant cubed x dx is half secant x tangent x plus half natural log of secant x plus tangent x plus c. Now this is the last question. This is the last example out of this first half of this section. So it's obviously a little bit complicated. I have given that problem on a test before. Now I did, like I showed the students in class and then I gave it to them on a test. I'm not saying I will give it to you. I'm just saying like that to me is not out of bounds. Giving you a problem like this one of something you've never seen, that would be out of bounds, because for you to come up with this one, unless I'm asking you that exact problem, that I don't expect of you. But if you go back and you kind of look at everything here now and run through this problem again, the first step of splitting it up was actually correct. This step, I think you just would have been going in circles, going all over the place. The other way we went, I don't think would have worked. I'd have to run back through that again. I think what we did there is we turned this into tangent squared x plus 1, but I don't believe that that would help. We have to do the integration by parts, and then from there we have to, this right here, this move right here is just, it works. All right. How are y'all feeling?
Needs practice.
Yeah.
Can I see the last part of the answer? Real quick, 1/2. Okay, thanks.
Okay. Yep. All right, so we're ready now. We have finished the first half of this section, trig integrals. Okay. After we master the above concepts, master them, right? So we just learned them, right? You still have to go do the homework, right? But after we understand how all that happens and feel comfortable with it, we can use them, the methods, the concepts, along with an interesting type of substitution to find antiderivatives of some rather complex functions. These new types of substitutions are called trigonometric substitutions, or what I will refer to as trig sub. So we've done substitutions, right? We've looked at an integral. We said, oh, we're going to say u is equal to something in the integral. We've done it a couple of times today, right? Mm-hmm. This is a different type of substitution that we're about to learn. We're going to take something in an integral that's not complicated, and we're going to replace it with something complicated. We're usually trying to go the other way around. We're usually trying to take something complicated and replace it with U to make it nicer to look at. Here, different. We're going to take something nice and make it ugly, and there's a reason why, okay? So here's the general idea. Let me do this on separate page. All right, so here's a general idea. I don't want us to be thinking integral or anything else right now. All right, I just want us to look at something algebraically. Let's say that I gave you, geez, can't even draw the square root. Let's say I gave you this expression, 4 minus x squared. All right, don't think integral, just there's an algebraic expression. Now, you cannot split this up, right? This is not square root of 4 minus the square root of x squared, right? That's like a huge no-no. You can't do that, right? So looking at this expression, maybe there's something I can do, some sort of substitution I can make to make this expression just a little bit nicer to look at. So I'm about to make a substitution. I'm going to let x be equal to 2 sine theta. Now, you're like, what? Why in the hell are you going to let x be 2 sine theta? Well, just hang on, all right? Let's see what happens. If x is going to be 2 sine theta, then tell me what x squared would be. Well, square that expression, you get 4 sine squared theta, right? Okay, so let's rewrite this then. What would this become if I make that substitution? Square root of 4 minus, and what did we just say x squared was?
4 sine squared theta.
4 sine squared theta. Now, both of those have a 4 in them, don't they?
Mm-hmm.
So I can pull a 4 out, factor a 4 out, and I'm left with 1 minus sine squared theta. But what is 1 minus sine squared theta?
4 cosine.
Cosine theta.
Cosine
Cosine squared theta.
squared theta. So this is the square root of 4 cosine squared theta. But now you have multiplication, you don't have any subtractions anymore. So now you can take the square root of each one of them individually. So what does this become?
2 cosine theta.
2 cosine theta.
The hell?
Right? Now, we no longer have x, do we? Like, we don't have an x anymore. But imagine now that I was asking you to do an integral of this. You would be stuck here. But making a substitution, your integral now becomes a cosine integral. What would you rather do? A complicated radical expression or a cosine trig function? Trig, right? Trig all day. Antiderivative cosine sine, we're done, right? Like, the integration will be easier if we can somehow take this algebraic expression and convert it into a trig. So we are going to make a substitution that we are calling a trig substitution. Why is it called a trig substitution? Because we're replacing something with a trig function, all right? That's the general idea of how this works, all right? Now, let's generalize it a little bit because that was a specific example. Imagine we had an expression look like this. A squared minus x squared. So this time, a is just some constant. A is a constant. The substitution that I'm going to make is x equals a sine theta.
Is that given or?
Yes, I mean, this will be, don't think about what's given yet. Just follow me algebraically. Like,
Okay.
if we have this expression, I'm going to make that substitution. X is equal to a sine theta. And let's see what happens. What would x squared become?
A squared sine squared theta.
A squared sine squared theta. If I come back over here and rewrite this, I'll have square root of a squared minus what we just said, a squared sine squared theta. What can we factor out?
A squared.
A squared can come out. And what will be left in there?
Cosine square.
Yep. That will turn into 1 minus sine squared, which will guarantee switch over using the Pythagorean identity. And that just turns into A cosine theta. So in the previous problem, the previous thing that we looked at up here, I'll scroll up in a second. Let me put this in a green box here. In the previous little part here, we had 4 minus x squared. We have to realize there that the 4 is actually 2 squared, right? 2 squared. So the A, the actual A that I had here in this problem, this right here, 4 was equal to A squared, which means that A was actually 2, which is why I put a 2 there.
Yeah, so I had a question regarding that. Could you have done it like initially, like the squared, like make it a 2 square?
Yeah, you can do that if it helps you see it.
So
And
what
then
if
use the property is the A square minus B square one, like, and expand it? Could you do it like that?
No, because then you'll have the product of 2 binomials and you still won't be able to do anything with that.
Okay.
Who else said something? Minato?
so yes, so what if A is not a perfect square?
Okay, let's see.
Could we say that that is actually A and we could square it?
Let me just do an example.
Okay.
Before I do that though, let me just, in the green box, here's what we're saying. If we ever see an expression that looks like this, the square root of some constant squared minus x squared, if we ever see anything like that ever, right? We can always replace the x with A sine theta. If we do that, this whole complicated ugly thing is just going to turn into A cosine theta every single time. Do you all understand? So let's do another one, and let's use something that's not a perfect square. Right? So all you have to do this is realize that 5 is actually the square root of 5 squared minus x squared. So what's A for us?
Square root of 5.
Square root of 5. Right? 5 is actually the square root of 5 times the square root of 5. So here A would be square root of 5. So our substitution would be x is equal to A square root of 5 sine theta. And without doing any work, what can you tell me all of that's going to turn into? What is all of this going to turn into at the end of the day?
Square root of 5 cosine theta.
Square root of 5 cosine theta. See, I'm not going to go through all the work. I already know that's what it's going to turn into. That's why I chose A sine theta, because the algebra will always lead me to A cosine theta when I'm done.
I had another question. Why is it sine, by the way?
Because of, that's a great question. The reason why it's sine is because we, by design, because there was a minus sign here, by design, we know that we will be able to factor the A squared out and we'll be left with 1 minus sine squared theta, which allows us to switch to cosine. You could actually do it the other way around, do A cosine theta, and then this would switch into A 1 minus cosine squared, and that would switch to A sine. But with this particular format, we could do it either way. We could have done A sine theta or A cosine. Most textbooks do A sine theta. Okay? Now, we haven't done any integrals with this at all yet, right? So I want us to consider something else now. I want us to consider this expression. That is not the same thing, right? I've switched the order. So I'm going to make a substitution again, all right? I'm going to make a substitution again. The substitution I'm going to make this time is not A sine theta. It's going to be A secant theta. Now let's see why a secant theta is the substitution to make. What would x squared be? A squared secant squared theta, right? And now what does this expression turn into? Let's see, x squared, which is a squared secant squared theta minus a squared. And then I can factor out an a squared again. And what would I be left with in here?
Secant square minus 1.
Secant squared theta minus 1. And that is a Pythagorean identity, isn't it? What is that?
Tangent.
Tangent squared.
But isn't like if we use a cosine here, so it's 1 minus cosine theta, cosine square theta in terms of sine square. But isn't like
No,
if I
cosine wouldn't work here. Cosine wouldn't work because if you did cosine square, if you did cosine instead of secant, then this right here would be cosine squared theta minus 1, and that is not sine squared theta.
isn't it the same thing? 1 minus cosine theta,
No.
cosine theta minus 1?
No, sine squared theta plus cosine squared theta equals 1. If I'm trying to rewrite this expression, I'd have to move the 1 over, which would make that cosine squared theta minus 1, and then I'd have to move the sine over, which would make it negative sine squared theta. And the problem with that is then we would have a negative under the root.
And we can't do that.
We can't have the negative under the root. So the appropriate substitution here is to do a secant theta. And if you do this, then you're guaranteed that this complicated expression is just going to turn out to a tangent theta, which again, I'd rather see tangent in an integral than all that nasty radical stuff. Okay?
So does this
Yeah, go ahead.
does this only work with radicals, or are there any other problem types that we could use this against?
This only works with square roots of a squared minus x squared, or x squared minus a squared, or a third option here that I'm about to show you, which is the one we haven't considered. And that is, what if there's not even a minus between them? What if it's a squared plus x squared? Or because it's addition, it doesn't matter, you could write it the other way around. What about in that situation? If
I
we
would
wanted-
use sine or cosine here.
Sine or cosine?
Yes.
It's going to be tangent. Let's see why. Let's see why. Oh, sorry, I forgot the A. Okay, because if we square that, we get a squared tangent squared. And now if I rewrite this, it becomes square root. Let me do the first one. A squared plus a squared tangent squared theta. Factor out an a. Factor out an a squared. And we'd be left with 1 plus tangent squared theta, which by definition is secant squared theta. And so the square root of that is just a secant theta.
What if you change the positioning, make x squared plus a squared?
Same thing happens. All it does is changes the order of these two things. It'll become tangent squared theta plus 1 instead of 1 plus tangent squared theta, which is the same thing as secant. Secant squared is the same thing.
So why is it, like I'm confused. We can use 1 plus tangent squared, tangent plus 1, but like we can't use that cosine is because that's
Well,
like
because the negative sign, look, the Pythagorean identity is this. That's the Pythagorean identity, right?
Mhm.
If you switch the order of these, it changes nothing. because there's addition there, right?
Oh, I see.
Tangent squared theta plus 1 is the same as 1 plus tangent squared theta. But when you're dealing with the sine cosine, if you move something to the other side, it becomes negative. We're not moving anything to the other side. We're just simply commuting the addition, just switching the order.
I understand. Yeah.
Okay. So let's get to the formula sheet. Maybe this will all make more sense now. Let's say that somewhere within our problem, we see a square root of a squared minus x squared. Somewhere within the integral, anywhere within the integral, we see that expression. We are going to make this substitution. Okay? Now, nowhere on this table does this help you to know what this becomes. But can you tell me what that's going to become? That complicated expression becomes what?
A sine theta.
A cosine theta,
Cosine.
right? Okay, now I did this in a different order. Shut up, man. Stupid dog. My wife's dog drives me crazy. I swear, once they both get going. Hey! I was nice enough to let him be in here with me, and that's what he does. It's the respect he shows me. All right, so the second one I did was this one. If it's x squared in front of the a squared, right, flipped around, then we make this substitution, and do y'all remember what this turns into?
Tangent.
A tangent, right? And then the last one we did was this one. And if we make the substitution x is equal to a tan theta, this becomes a secant theta, right?
Mhm.
I'm going to be nice to you. I'm going to allow you to add this to your sheet, okay? This gets added in. So you can add this and this and this, all right? That way you don't have to remember what they turn into.
Okay.
All right, you ready to see this bad boy in action now? This trig sub is so powerful, but man, these problems can get pretty complicated. So it's about to do it. There we go. We're gonna do that one. X cubed 16 minus x squared. Okay, so you're sitting here and you're looking at this, and maybe you're thinking basic U sub, because you see an x cubed, the derivative of that's x squared. You've got an x squared. Oh wait, it's trapped under the root. You can't do that, right? So then maybe you're thinking integration by parts. Good luck. Good luck. Integration by parts. I don't see that going anywhere soon. All right. But you see a square root, and you see a squared minus x squared. Do you see that?
Mhm.
So this is perfect for trig sub. I'm going to take x and replace it with a sine theta. What's a for us here?
4.
4. So I replace it with 4 sine theta. Now, what do we know about the square root of 16 minus x squared? All of that is just going to turn into what?
16 minus 16 sine square theta.
4 cosine.
Yeah, but I'm not going to do
theta.
that. I'm just going to jump right to what it turns into.
4 cosine theta.
Oh, 4.
Cosine theta. Right? Yes?
Mhm.
Yes.
So I'm going to be able to replace everything in yellow right now with 4 cosine theta, right?
Mhm.
I'm also going to be able to replace that x, which still needs to be raised to third power, with 4 sine theta. right? I'll replace the x with 4 sine theta. What's the one thing I've not replaced yet?
The cube.
dx.
Well, the cube will be taken care of when I plug the green part in,
No, the dx.
the dx. And guess what? You can't forget this part either. And we haven't talked about this part. What we need to figure out is what is dx. So what we do is we take x, take that equation, and we just take the derivative of it with respect to theta. So we're going to get dx equals 4 cosine theta d theta. I'm differentiating that equation implicitly with respect to theta. So I'm really doing this, dx d theta equals 4 cosine theta, and then I'm multiplying both sides by d theta. We've done that a lot, so I think that's probably okay that I'm just going to throw that in there. Okay, so there we go. That's the blue. We should be able to plug everything in now. Let's do it. Integral. The x is 4 sine theta. Still need to cube that. The square root part turns into 4 cosine theta. And the dx turns into 4 cosine theta d theta. Does everyone see all the pieces have been put together? We have taken this rather complicated algebraic integral involving square roots and x cubed, and we turned it into a trig integral, right? It's a trig integral now. Okay, so all these 4s are driving me a little bit crazy. I have 4, I'm gonna have to cube the 4, right? It's like 4 cubed, then I have another 4 and another 4. That's gonna be 4 to the 5th power, isn't it? 4 to the 5th power. I'm just gonna take that and take it outside of the integral. I'll get my calculator out in a minute if I need it. 4 to the 5th power. And now let's talk about what's in here. Sine cube theta, cosine squared theta, d theta. Everybody follow that?
Mhm.
No, that's what I thought. This is 1024. Okay. Now what?
There's a rule that we went over last class, no? About
Yeah, that's
this?
right. That's right. So remember, I pointed this out. After we master the above concepts, right, we're ready for trig substitution, which now we're trying a trig substitution problem. So now we've got this thing in here. We've got sines and cosines mixed up together. So I've got to maybe go back and look at my formula sheet. Let's look at last class. I think it's sitting here somewhere. Where is it? I don't even know. I thought I copied and pasted it here. I could have gotten to it already. Go back to the formulas. Here we go. Blah, blah, blah. Here we go. Okay. So we have, first thing we look at is, do we have cosine to an odd power? Then
No.
do we have sine to an odd?
Yes.
We do have sine to an odd? Okay. So what does it say to do when we have sine to an odd?
Take the factor and use sine square equals 1 minus cosine square.
Factor of what? Take one factor of what?
Sine.
Sine, right? So at this point, I'm going to say this is 1024 integral sine squared theta times cosine squared theta times sine theta d theta. So I went ahead and peeled off one factor of sine. This part right here, sine theta d theta, is going to be, I'm thinking ahead. I'm about to do a basic U substitution. And I'm thinking, okay, U is going to have to be cosine then, because that's the derivative of cosine. We're off by a negative, but who cares? So that means everything else has to be rewritten in terms of cosine. 1024 integral 1 minus cosine squared theta times cosine squared theta times sine theta d theta all I did there is replace sine squared with 1 minus cosine squared. And now I'm ready for a basic U substitution. The U is cosine theta. Du of that is negative sine theta. I'm going to go ahead and move the negative to the other side now. You'll just stop me if I'm doing anything that you are lost on here. Replace all the cosines with u's. Replace sine theta d theta with negative du. I pop the negative to the outside. Distribute the u squared through. I'm down to a polynomial now. Power rule. So now it's time for the antiderivative. So let me go ahead and just 1/3 u cubed minus 1/5 u to the 5th plus c. Am I done?
No.
No, I've got to replace u with what?
Cosine theta.
Cosine theta, right? Let's distribute that through. Let's distribute the 1024 through. Negative 1024 through. I've got some negative negatives that became positive there. Okay. Any questions up to that point?
No.
Am I done now?
Mm-hmm.
Am I? Was our original problem in terms of theta?
No.
The original problem
Terms
was
of
in
x.
terms of x. So your answer needs to be in terms of x. Crap, how are we going to get back from this to x, right? How do we get from here back to x? Let me show you how. We go back to the substitution we made. That was our original substitution, right? That was our trig substitution. And I'm going to come down here. I'm going to write that down so that you remember what I did, what we did. We made this substitution, right? Now I'm about to do something, and when I do it, I hope that you remember something we did at the very beginning of this class. I'm going to divide both sides by 4 first. And now I'm going to create a reference triangle. So this was my original, that's the relationship I have between x and theta, right? That's the connection I have. So I just isolate sine theta by itself, say that it's x over 4, and then I just draw a little right triangle. I label this angle theta, and I just remember that sine is opposite over hypotenuse. So that means this side is 4 and this side is x. And that means that the adjacent side has to be the square root of x squared minus 16. Yes? No.
Yeah, plus.
Hold on a second. Sine.
The opposite is x.
Pardon me?
The opposite is x, and the
Yeah, I switched. I don't know why. I just had a complete like brain fart. I don't know why I put 4 on the opposite side. Okay, that's x and that's 4. Okay. Opposite over hypotenuse. I said it, I just wrote it wrong. And that means this side is 16 minus x squared under a root. So I'm trusting all of you that you know how to get this side, right? Just use the Pythagorean identity, a squared plus b squared is c squared, solve for that side, yeah? Now, why did I do this reference triangle?
To
We
find
wanna know
cosine theta.
Cosine, cosine.
We want to know what cosine theta is, right? We know what sine theta is, and using the triangle, we can get what cosine theta is. Cosine theta, according to this triangle, is adjacent over hypotenuse, right? Adjacent over hypotenuse. So now we're ready. Negative 1024. Shit. You know what? I kind of wish, you know what? I'm not going to wish. I'm going to do it. I'm going to force that thing back. Do you remember that 1024 was really 4 to the 5th power, wasn't it?
Yep.
I'm going to push it back to 4 to the 5th, and we'll see why in a second. Over 3 times now cosine theta, so it's this thing right here, cubed. So that means I'm going to have the square root of 16 minus x squared, that thing cubed, and then I cubed the bottom also. 4 cubed. And do you see why I did that? Because I'm going to get these 4 things to like cancel out and become nicer. Plus 4 to the 5th over 5 times square root of 16 minus x squared over 4, oh, I forgot to raise that to the 5th power, 5th, over 4 to the 5th plus c equals, okay, 4 cubed, 2 of these, 3 of those go away, I'm left with 2 of them, so I get negative 16 thirds. And then watch how I write this, 16 minus x squared to the 3 halves. Right, so if you have the square root of x and then you cube it, that's the same as x to the half cubed, which is the same as x multiply those powers 3 halves. So I'm just rewriting the square root of something cubed to be that something to the 3 halves. Plus, let's see, these cancel completely. 1/5 16 minus x squared to the 5 halves this time, plus c. Bam. So welcome to Trig Integrals. Welcome to Trig Substitution. There's a lot going on here. And this is only our first example, so we will definitely get more practice with this. All right, but this gives you a real flavor of what this is like. A lot to do here. What do y'all think? It's pretty awesome, isn't it? I mean, that's a pretty awesome technique. I mean, because really, otherwise you'd be stuck here. You just wouldn't have anything you
That's
can do.
like 3 different things we're doing in one problem. Substitution, like if it gets more complex, can we do like integration by parts in the same problem?
Yep. So do you remember me promising you that this would happen? Do you remember me telling you, like, we're going to build up these techniques, but then when we get towards the end, we're going to be doing problems that require like all of them?
Mm-hmm.
We're kind of getting there. We're pretty much there. Okay.
I had a random question.
Yeah.
Never mind.
Never mind, or you forgot?
No, I was gonna say, like, could you every problem where you have to use the sign to get the substitution,
Mm-hmm.
could you technically just go back to the top and pull that out
What do you mean?
without having to like do the reference triangle? Because I mean that's the same thing as what we used in the bottom for cosine, except to the 4th that we put over there.
Oh, here? This right here?
No, this over here.
What?
So it's like that over that.
It's what over what? I'm not sure what you're saying. On this reference triangle?
Yeah. So it's basically that over that, the opposite over hypotenuse. But that's so like what I'm saying. All I'm saying is I'm trying to find a shortcut so I don't have to draw a reference triangle.
Okay. I would strongly recommend you draw a reference triangle.
Mm.
And the reason why is because there are going to be problems where you might be sitting here and you might have some information about sine, right?
Mhm.
but your answer has cotangent in it or secant in it.
Mm.
So you may know what sine is, but how are you going to recover what tangent is? The only way you get that is the triangle, you know? So it's just dangerous. Look, you've done this much work, right? A triangle at the end is not going to kind of like, it shouldn't make or break you, you know? Like this should be, at least you get to draw, right? So it's kind of fun. You get to draw a triangle. I don't know.
Well, if you made a mistake right in there, everything else is wrong, pretty much.
Where this?
Yeah.
Yeah, you messed that up like I did a minute ago. Now, the reason why I knew I messed up is because every single time you do a reference triangle, and I was going to wait to tell you this, but I'll tell you now, every time you do a reference triangle, one of the sides is going to be your original square root thing. See that thing?
Mm-hmm.
That
So
is
it's saying
going to wind up being a side.
Same.
Yeah. We're running low on time here. I want to do one more thing, but let's just be clear on the homework. You should be able to get through, well, you should attempt everything in 6.2 up through the first 36 problems are all trig integrals. Trig integrals. Now, I don't think I'm assigning you that many, but you should not try and do anything, well, maybe try number 39, 40, and 41. You can try those, 39, 40, and 41, because in those problems, they actually tell you what trig substitution to make, and that might be worth your time. But you definitely need to get the trig integrals done for homework because, like I said, you can't do this if you can't do the trig integrals. Can't do trig sub if you can't do trig integrals. All right, so I have like 3 minutes left. I'm going to differentiate this. You ready? Take derivative of this. 3/2 comes out. When I do the 3/2, it becomes -8. -8, 16 minus x squared raised to, I subtract 1 from the power, so that's 1/2, times the derivative of what's inside, which is -2x. Okay, plus, now, derivative of this piece, 5/2 comes out, hits the 1/5, becomes 1/2. Then I have 16 minus x squared raised to the, I subtract 1 from that, so I have 3/2 times the derivative of what's inside, which is -2x. Okay, clean up a little bit here. 16x times, yeah, I'll do it that way. This is just the square root of 16 minus x squared. Minus, I put the 1/2 and the 2x together, I just get a minus x. And then this expression is really the square root of 16 minus x squared, all of that cubed. And now what I'm going to do from here is I'm going to factor a GCF. I'm going to pull an x out of both, and I'm going to pull a square root of 16 minus x squared out of both of those. So what I'll be left with here is when I pull an x out and pull that root out, I'm left with a 16 minus, okay, when I pull this x out, it's gone, and then I'm going to pull one of these factors out. If I pull one of those, I'm left with 2 of them. So I'm going to have a square root that's being squared, which means it's going to make the square root go away. So I have minus 16 minus x squared like that. And then when I do the algebra here, the 16 minus 16 goes away, but that negative passes through there and becomes an x squared. So everything in brackets becomes the x squared, and I still had an x out here, so that becomes x cubed square root of 16 minus x squared, which is the original integral. Right? So we just checked that that is the correct antiderivative. Well, that's good then. We did it right. All right, so we have fun days ahead of us. We have fun days ahead of us, yes? So just, you know, at this point, keep up with your homework. And, you know, I still haven't had any visitors to my office hours. Are y'all doing any study groups or anything? Or are y'all putting anything together? No?
There was an email for an invitation for
Yeah, I made a
Yeah,
group me,
so-
but it hasn't been active.
Okay, yeah, I mean, let me see here.
I still have some catching up to do on the homework. I've been working on some other stuff from other classes.
Same.
But I figure I'll probably have a couple of questions, so I may
Look at that
see you
right
in a
there.
couple of days.
Look at that. Do y'all see that? Y'all can see this, yes?
Yeah.
That's the first question off of exam 2 from a year ago. What type of problem is that?
The same one we're
Trig sub.
actually working on. Yeah.
That's a trig sub problem. Why do you think I'm not giving them a trig integral to start the test?
To see if they actually, if your students actually did work
Well,
on
I mean-
mastering.
Yeah,
Yeah, I mean-
they did their homework.
Don't they have to do a trig integral? Right? Like you're not doing this problem unless you can do a trig integral. So I don't need to test you on trig integrals. I only need to test you on trig sub. It's built in, right? It's built in. So most of this test is trig integrals.
So the exam 2 is more trig integrals.
Yeah, because you can't do anything without, you can't do these without the other stuff. So, you know, look at that question. Let's make that your first quiz. All right?
Okay.
Maybe that'll motivate you to try something different. Let's just say, you know, next time we meet, I want you to have that problem worked out and have it with you in front of you. Okay?
Okay.
That'll be our first quiz grade. Shall we peek at the next one?
Yeah.
Yes.
Where is it?
You were right about the fact that the U substitution and
You're not ready for that yet.
integration by parts will look easier.
It's relative, right? It's all relative. You know, you start to, it's relative by necessity almost, right? Like by necessity, these other things have to become easy things. Like power rule. Think about power rule. First time you ever did like x to the 4th power, what's the antiderivative? It's like 1 over n plus 1, x to the n plus 1. I mean, now that's just, you know what I'm saying? Like everything just has to become something that you can, yeah. Now, look, the trig sub will never become like, oh yeah, that's easy. Like trig sub is always difficult. Like it's always a lot of stuff you have to keep track of. So, all right, look, the good news is we're kind of at the difficulty level. We're like, in terms of integrals, we're like reaching the peak of difficulty for what we're gonna do. Like if you can get through trig integrals, you should be okay with the next section. And then from there, we get a little bit of a break. When we do applications, it's a lot more visual, and I think things will go better. So, okay, work on your homework. Have a good day.
Wait, do you know when around the next test would be? Like test number 2?
I don't. I know it's on our schedule. Let's see if we're sticking to this, but I think we're already behind on this, aren't we?
A little bit.
On the 13th. We're going to have exam 2 when we finish this information.
Okay.
Today's the 20th.
Now, I may not do all of 6.6. 6.6 also has 2 parts to it. So I might just do the first half of 6.6.
Okay, but it's still like around the beginning of October.
Yeah, October-ish, mid-October.
Okay.
Yeah. Okay, keep up with your homework. Come visit me during my office hours.
All right.
All right.
Thank you, Professor.
Have a good day.
Thank you very much.
Have a good one.
Nice day. Thanks.
Sure.